So far we have talked about redirection mechanisms and authentication mechanisms. Now we will talk about load balancing, which is the process of distributing loads of user requests to different nodes. I will describe how load balancing happens in Akamai, which is the biggest CDN. And this description is based on a paper written by Akamai engineers. So we can trust this is what really happens in Akamai. So a CDN is organized hierarchically. There are clusters distributed around the world, and within each cluster, a set of servers. So we need to distinguish global load balancing, which means deciding to which cluster we should send requests, and local balancing, which means choosing which specific server within a cluster we should use to serve the demand. Let's start with global load balancing. So first, they divide traffic into classes: video, image, software, download, web page, etc. Each class, as you can imagine, has different requirements. For instance, video needs a lot of bandwidth, while loading a web page needs shorter latency, because we want the page to be retrieved as fast as possible by users. Otherwise, they will abandon. And there are all a sort of range of requirements. Then they create tuples. A tuple actually is a pair composed by a traffic class and an origin. The origin is represented by a subnet, the IP address of a subnet. And actually, each subnet corresponds to a certain set of customers of a certain region of a certain access network. So actually, in a tuple, we take into account not only the nature of the traffic, but also the geographical origin of the traffic. And then we need to associate each tuple to each cluster. This is a classic matching problem, let's say, because on the left we have tuples, and on the right we have clusters, and we want to associate them. Clusters have different resources in terms of memory, CPUs, disk, bandwidth available, etc. And tuples have different demands. That is the amount of requests of that tuple that is expected. And on the one hand, we would like to associate each tuple to the best cluster in order to satisfy the requirements of the tuple as best as we can. For instance, we may like to associate each tuple to the closest cluster. But on the other hand, we should also take into account that clusters have also preferences with respect to tuples. Because if a cluster wants to serve a certain traffic tuple, this has a cost. The cost is mainly related to consumption of resources and also to the payment the CDN has to make to the access networks. So if this cluster is in a certain region of Europe, CDN has to pay the access network there. Another cluster in Africa, for another cluster in Africa, CDNs have to pay for the traffic produced the access network provider there. So each cluster needs to spend a certain cost that is different from a cluster to another to serve a certain traffic tuple. So we have two contrasting preferences. The ones for which we want to serve traffic tuples as best as we can and associate them to the best cluster possible. On the other hand, we want to serve the demand in the cheapest way possible. So when we have this kind of contrasting preferences, we can model this problem as a marriage problem. This is a classic matching problem. in which we have on the one side men, which have certain preferences toward women, and on the other side women, which have preferences toward men. And these preferences are in general contrasting. So we want to end up with a stable matching. A stable matching is a set of marriages, where each man is married to a woman, vice versa, and we want the set of marriages to be stable. This means that we don't want that marriages break and new marriages form. This means that we don't want to end up in a situation in which a certain man A is married to a certain woman and another woman B is married to another man, but actually A prefers B over the current partner, and B also likes another man over likes A more than her current partner. This is an unstable matching, because in this situation everybody would be better off by switching the marriage, by letting A marry B and the other woman marry the other man. So we want to end up with a stable matching in which this situation doesn't arise. How can we do this? So there is a very simple algorithm that is guaranteed to end up with a stable matching, a stable set of marriages. And this algorithm is iterative. In each iteration, we let a man choose the preferred woman, and the woman will accept if and only if the new proponent, she prefers the new proponent more than her current partner. If it is the case, the woman will accept the new partner and will break her current marriage. And also the new partner will break his current marriage to marry the woman. So it can be shown mathematically that at the end the set of marriages will be stable. Nobody will want to change marriage. So the same situation can be translated to our load balancing case. Because in this case men are traffic tuples and women are clusters. There is, however, some difference. So while in the stable marriage problem one woman can be married by just one man, in this case we want clusters to be married by more than one traffic tuple. Okay. And also another difference is that we have to take into account these capacity constraints that is multidimensional. So resources are CPU, memory, they are diverse. So we have to modify the stable marriage problem in order to take into account these differences. But the concept is the same. So one modification of the stable marriage problem is relies on the resource tree. A resource tree is a way to describe resources of a certain cluster. This tree, for instance, is describing a certain cluster, and it is saying that 50 bytes per second are available there, 30 flops per second are available there. Flop is like an abstract way to indicate CPU processing capabilities. And then we are also saying here that this cluster is able to serve 30 flop per second for video traffic, 40 for web traffic, 30 for apps. This is representative of the fact that certain clusters may have specific hardware that offer capability suitable for certain type of traffic. For instance, codecs, encoders, video encoders, etc. They may be present in one cluster more than in another. So a certain cluster may be able to serve video traffic more than another cluster. So in this way we are representing the capabilities of a cluster. Now suppose there is a demand for this traffic tuple. okay, with this origin and of a nature video, okay, of a class video. This traffic needs 30 bytes per second and 10 flops per second. So we can associate this traffic tuple to this cluster, and by this we start to consume some resources. Okay, in fact we consume 30 bytes per second, and in particular we consume 30 bytes per second for 10 flops per second, and in particular 10 flops per second for video. Then another demand comes which needs these other resources, and we can map it to the resource tree, because there is still the demanded resources are still available. Now suppose another demand comes which needs 40 bytes per second. Well, there are no 40 bytes per second available in this cluster, so we need to decide whether to reject this demand or to accept it. Well, if this demand is preferred over the first one, which means if for the cluster is cheaper to serve this green demand instead of the blue demand, well, the new demand will be accepted. So first the blue demand will be rejected. It's like we are breaking the marriage between this cluster and the blue man, and we accept the green demand, and then we go on with the new demand coming. So I hope now you have an idea of how we can associate traffic tuples and clusters. So we can simplify by saying that each traffic tuple is associated to the closest cluster, but as you have seen, this is not what happens, what always happens. Sometimes we may associate a traffic tuple with a cluster that is far away, if it is cheaper to serve the traffic tuple, or if we have already exhausted all the resources available in the closer cluster. So in order to decide properly this association, CDNs run these kind of matching problems. Now, suppose now we know that we want to serve a certain traffic tuple with a certain cluster. Now we have to decide which of the available nodes in that cluster we want to use. And one simple way to do it is that we associate to each content provider an ID. So remember that a CDN is serving content for different content providers. Akamai may serve content of Facebook, of Amazon, of BMW, etc. So they have different customers, different content providers. So they associate to each content provider a separate ID, and then they compute a hash function on this ID. The simplest hash function that you may think of is modulo. So they compute ID modulo n, where n is the number of nodes available. This will result in a number indicating 1 on the available nodes. This means that all the traffic directed to that content provider will be served by the node resulting from this hash function. So this is a way of load balancing the traffic within a cluster, and as you have observed, this is very simple. You get requests, you compute a hash function, you decide where to send these requests. Of course, things are more complicated. Okay, the hash function is not really the modulo that I've shown you. It's a function with more properties, but it's just a detail here. And also, it's not true that we associate each set of requests to just one node. We usually use multiple nodes to be robust to failures, and also to avoid that one node is overloaded in case, for example, one content provider absorbs a lot, is attracting a lot of traffic. But the idea is there.